Okay, so in this video, we are going to apply the confidence interval to the most famous example, the presidential election prediction problem. So, and the problem is, so I'm using the presidential election in 2012. So after that election, the prediction was not accurate and very more much became more complicated, not as clean as this. So please understand, I tried to update it, but just to be politically safe, and also these days the prediction is not reported in this simple way. So that's why I cannot find a clear example like this. So please pardon me. Anyhow, this is from CNN in like 2012, and the survey was conducted in September, and the sample size is 783, and the margin of error is 3.35% point. So what it means is the expected estimated percentage support for Obama was 50%, but this is point estimator, but you have to allow plus minus 3.5% margin of error on top of this. So Obama's support for Obama at that time was in between 46.5% up to 53.5%, right? So what is missing in this, in CNN was the confidence level. But usually when it is not stated, that means confidence level is the conventional one, 95%. So later we are going to come back to this case, and we'll find 95% explains those numbers. Okay, so let's think about the underlying distribution. What we can think about is the underlying experiment is randomly choosing a voter. I randomly find a voter and ask about her willingness to vote for a certain candidate. Like, would you like to vote for Obama, or yes or no? It's like that, right? Have to choose. In the questionnaire, there must be answers. So I will simplify the problem to a binary case, right? It is yes or no question. There are actually more than two choices, but for the sake of exposition, I'm going to simplify. It's yes or no. Yes, I support the candidate. No, I don't, right? It is binary. So one is one if you support a specific candidate, and zero not. And we are interested in the percentage of voters who support this candidate, right? That is in binary distribution, that is the parameter P. P is the probability of success, and we are interested in this. What is the underlying among the population? What is the probability of success supporting this candidate? The problem here is what we learned earlier in the previous video was an estimation procedure for the mean. We restricted our focus on mean estimation. We would like to estimate the unknown mean, but we are now interested in the probability of success. However, in this case, in this specific example, it does not matter because remember, in binary distribution, the mean is the probability. So if you are curious about probability, you can still estimate the mean, right? So I was curious about the probability, but you can apply the estimation procedure for the mean. So in that sense, learning estimation for mean is pretty much okay. Like, it is applicable to more than you could imagine, right? So it covers a lot of examples. Anyhow, we are going to apply the estimation for mean and interpret that as probability in the end. Okay. Another thing is, here we have to think about the standard deviation, but the binary distribution specifies the standard deviation in this form, right? You may remember there is only one parameter for binary distribution, so there is no separate parameter for standard deviation. If p is determined, then automatically the variance is p times 1 minus p, so the standard deviation is its square root, right? This is the standard deviation. So you have to reflect this formula to your confidence interval. When you calculate confidence interval, you need standard deviation. Then to calculate that, we are going to use this formula. Let's see. Okay, now let's think about a simpler numerical example. Like I'm going to say I'm doing like prediction, the same presidential election prediction, and I will calculate 95% confidence interval for say something for a candidate, and I surveyed 400 people, 400 likely voters, and I found that 320 of them support that candidate, right? So 320 said yes, they are success. Then, like based on these data, let's calculate the confidence interval using this formula for the mean. Okay. So remember, we need to calculate 4 numbers to construct an interval. But so first, sample size is already given. We observe 400 voters, so it is pretty simple. And z alpha over 2 is determined by the confidence level, 95%. So you can look up the table and find the number here. And sample like that, the only thing we need to calculate is the sample average and the sample standard deviation. Let's do that. Samples average. The sample average is, remember, the sample probability of success by the feature of the property of the binary distribution. So 80% of people said yes. 80% was yes. That means that is the probability, but at the same time, 0.8 is the sample average. Sample average is 0.8. Okay? And standard deviation should be calculated following the binary formula like this. And the P is probability in the sample, which is 80%. I calculated ahead. That is, then you just plug in this into calculator and see, you will get 0.4. I chose the numbers so that we get a simple number as a result. So standard deviation is 0.4. Sample size 400, which also makes a simple square root. And finally, 95% implies 1.96 as before, right? If you can follow up to here, it's nearly done, right? So then combining those 4 numbers, you can calculate the marginal error, right? 1.96 multiplied to the standard error. Standard error is standard deviation divided by square root n, right? That is this. Plug in those numbers, 1.96, standard deviation 0.4, square root of sample size 20. So you will get 0.0392. This means 3.92% point, right? Marginal error is 3.9% point, which is reasonable, right? Like we often see some like marginal error similar to this. And the point estimator is the sample average, 80%. So my point estimator is 80%, but you have to allow plus minus 3.92% point. So in the end, the estimated approval rate or support rate is between 76.08% up to 83.92%. That is the interval estimation, right? And this will contain the truth with 95%. That's how we calculate that. And as you see, application is pretty simple, right? Just calculate the four numbers correctly, right? Should be pretty straightforward. Now, we will apply the same idea here again. We would like to reduce the margin of error, like design. We'd like to design the survey so that the margin of error is 3.5%. So we can survey more people to make our estimator better. Still, confidence level is 95%. What can we do? We have to think about this inequality. The margin of error should be smaller than 0.035. This is our new goal, and we are looking for the sample size n that satisfies this inequality. But the alpha is fixed at 95%, so z alpha over 2 is fixed at 1.96. It does not change, but inequality must be satisfied by increasing the sample size. Okay, then move the square root n to the other side and bring this to the denominator to have this inequality, and then square both sides to have this inequality, which shows the sample size must be greater than this, which means you need to have at least 502 observations. Then you can reduce the margin of error to 3.5%. That's how we can apply the survey design idea in here. Now it's your turn. You need to do it by yourself. So I changed the number. I surveyed 400 likely voters, and I find 200 of them are supporting a certain candidate, right? So in this case, what is the margin of error for this prediction at 95% confidence level? You have to do it by yourself. Again, remember, be careful about calculating the standard deviation. Otherwise, pretty much the same as before. Okay, so let me turn the page. So I will use the same z alpha over 2 because 95% always implies 1.96 approximately. And the standard deviation is given by this, but the P is like 200. The probability of success in this survey is that 200 out of 400, which is 50%. So 50% times 50%, square root of that is 50%. Standard deviation is 0.5, and sample size is 400. We surveyed 400 people. So plug them in, then you get the margin of error. Now, the margin of error does not require the sample average, so you only need 3 numbers. So the answer is D. That means, as a result of this survey, you get 4.9% point margin of error, right? You have to allow a certain margin around the point estimator, okay? Now, I want you to reduce the margin of error by collecting more data, surveying more people, right? So your target is now 3.5% point, right? The margin of error must be smaller than 3.5% with the same confidence level at 95%. So now it's your turn again. Try what is the minimum required sample size to achieve this margin of error. Of course, the numbers, the data are the same like this. Okay, so let me show you the answer now. Pause it if you have not finished yet. We need to solve out this inequality for sample size n, right? 95% confidence level implies 1.96, and standard deviation is 0.5 as before. Must be smaller than 0.035, 3.5%, right? And then move around the terms and you get this. So you need 784 observations to make the margin of error 3.5% point. Okay, that is the number here. I think there must be some like a rounding error, but you can see that this survey was designed based on what we just learned. Maybe these numbers are rounded, so I don't know where the rounding error happens, but like approximation error, rounding error happens somewhere, like making one difference sample size. Anyhow, we can see that our survey design is applied in this political poll, right? So it is simple but pretty useful and widely used. That is just the starting point of the survey design. Finally, I have additional words. Like I just finished estimation chapter, but if you have taken another statistics course or if you are reading a textbook, you may wonder why my estimation chapter is different from those textbooks. Usually, textbook has two separate chapters where like they also consider estimation for the mean, right? I consider mean, but they divide two cases when the standard deviation is known and when it is unknown. Uh, but my answer is, I would say, how can we know the standard deviation without knowing the mean? You can make up some examples for this, but I think the first case is unrealistic. It exists only for theory. Statistical derivation requires sigma, so you have to assume this is known. But I think it's useless in practice, so I did not cover it at all. And 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 old school theory uses different distribution, different approximation to these different cases. That's why they divided those two cases. Typically, you must have heard about students' t distribution if you take another like statistics course. Most statistics courses still teach t distribution, but I don't use it at all because I have like I it's rarely used. And you can unify all those theory to central limit theorem, right? So under the central limit theorem, you don't need student t distribution. You can show that student t distribution can be also approximated to a normal distribution. So it's old school theory and requires more restrictive assumptions. So I don't use it at all. So student t distribution requires like the underlying distribution must be normal. It's not an approximation, which is good, but does not depend on sample size. But instead of requiring normal distribution, I use approximation based on the central limit theorem. It is great because, like for example, if the underlying distribution was rolling a dice, then student t distribution does not work. But I showed you, even you roll a dice, it will converge to a normal distribution, right? I simulated dice roll and it is still normal distribution. So, but student t distribution does not apply to that case. Instead, I require the number of observation must be sufficiently large. That is the only requirement. But these days, as I said, we have big data. Data size does not matter these days. Computation power is much better than when the theory was developed, right? So I think this is like this should be obsolete from any textbook, any statistics class. And instead, we need to focus more on the central limit theorem. So unify all the theory using the central limit theorem is the right way you have to learn. I believe, in my opinion. So that's why I do not use student t distribution at all. Still, its name remains in our class. like standardized, the standardization will be called the t statistic based on the student t distribution. So it is t, it is denoted by t, and we are going to approximate. So in the past, in the textbooks, these t thing standardized statistic was following student t distribution, but now we are going to approximate this to a normal distribution because this is the difference between t distribution and normal distribution. I don't know what is what. Blue and there are two distributions, blue and orange. One is student t distribution and the other is standard normal distribution. So basically they are pretty much the same thing. So you don't need to learn something new that is more limited. So I do not teach student t distribution. So I like it is my excuse why I don't teach student t distribution. In case if you already learned it, if you wanted to learn it more, then I'm sorry. And if you see me, come see me, then I will be happy to explain more about student t distribution. And if you want to learn more about why it should be obsolete, I am willing to talk about that more. So then please stop by during the office hour. And now, thank you for watching. This is the end of chapter 8. So from the next chapter, we are going to study hypothesis testing, which is very closely related to the estimation, right? Okay, see you later.